Hey everyone. As was stated, my name is Nick Jones. I'm a data scientist at Uber. I'm going to be talking about how we use Scala at Uber Data Science. And it should be, I hope, kind of a fun, high-level talk to see some actual application. And yeah, so I'm originally from the United States. I'm from Seattle. I worked at Uber for 3 years in the San Francisco and now Amsterdam offices. Before that, I worked at a firm that did expert witness testimony in court cases that involved statistics and machine learning, basically ghostwriting expert reports. And it was fun, but intense. And when lawyers are your clients and they have clients, things that normally would be crazy all of a sudden become reasonable requests, and it's no fun. So I like Uber. I'd like to talk today through a motivating example from my own work, through which we will talk about how we use Scala and experimentation and machine learning, which are kind of the main things that we do as data scientists at Uber, at least as product data scientists embedded within teams that build stuff, which I think is pretty interesting. And then, as a bonus, talk about how we use Spark Magic to directly interact with Spark through Scala through Jupyter Notebooks, which is kind of where people like me live. So let's talk about our motivating example first. Now, I work on the cash payments team at Uber right now, which allows riders to pay for Uber using cash instead of their credit cards or other digital payment methods. So why does this matter? Let's have a little story to start. Let's say you are living in Mexico and you don't have a great job. It's kind of hard to make ends meet. And you've looked and looked, and your friend finally scores you this job interview, which is really promising. It's going to be a higher paying job. It's going to be better. You'll have more time with your family. So you take the train into the city like you always do, but then the train breaks down. And no one knows how long it's going to be. You have to get to your interview. There is a bus, but it's a 20-minute walk, and it leaves in 10 minutes, and it won't come again for another hour. So that won't work. You can't walk there. So you hear people on the train say they're just going to take an Uber into this city. You've heard about Uber, you never used it, but you think, hey, this could get me there. So you download Uber on your phone, you're ready to go, and then it says, please enter your credit card information. Now, you don't have a credit card. No one you know really has a credit card. It's just not really a thing where you live. You get paid in cash, you pay things in cash, it's just what everyone does. I mean, if you really have to have a credit card, your uncle has one in a drawer if anyone needs to do something, but generally, credit cards are just not a thing. And this is the case for a lot of the world, actually. And so, because Uber doesn't take cash, you miss your job interview. If Uber does take cash, you get there with time to spare. And you could substitute Mexico for a lot of countries in Latin America, India, Bangladesh, Pakistan. This is pretty common. So only supporting credit cards made sense in early markets, but then when we decided to invest heavily in India, Latin America, the Middle East, all of a sudden, cash became a big thing. So why didn't we just always do this? Well, the answer is, it's not magical. That was the phrase that was used to describe the Uber experience and what cash was not. Because, yeah, I mean, the cool part about Uber is you just get there and you just get out. You know, it's nice. Just is taken care of. You get an email receipt and you just go on your way. You know, what about change? If you probably don't have 1783 on you. What if the driver doesn't have change? You know, then what do you do? Do you eat it? Do you like go to a convenience store to get change? You know, that's hard. What if you want to split a fare with your friends? I mean, you can, but if you don't have the money, that's hard. And then also, what about Uber's service fee? Uber is a platform which matches people who want to give rides with people who want rides, and they take a commission for that. That's how Uber makes money. And so if it's a credit card trip, you know, the trip is this much. Most of it goes to the driver. Uber takes some. But if it's cash, you can't just, you know, cut the 20-euro note. So how do you handle that? So clearly there are costs to cash. There's a reason Uber did not initially do cash. But as Uber grew and expanded internationally, it became a thing that we wanted to do. But because the costs were so high, we needed to know what is the actual benefit of cash. Because if we don't really get anything out of it, there are reasons to not do it. So how do we know exactly the benefit of it, and therefore we can justify it on a global scale? Because the thing about Uber is, if Uber does so many trips, a small change, compounded by tons of countries and 600 cities, that's tens of millions of dollars, and that's like Uber is successful or not. So we have to be pretty scientific about this. So the way we do this is experimentation. So now let's talk about how we do Scala and experimentation. Now, the reason we do experimentation is because the outside world actually has a larger impact on user behavior and therefore metrics than the things that you ship, usually. So you can't just ship something and then see what happens, because you have to have a control group. What if you ship something right before a festival? Then you're like, hey, yeah, this is great. Everyone's taking trips, my feature is awesome. Or what if you shipped right before Christmas and everyone's staying home? So you have to hold back a control group, and the control group has to be randomized between the treatment and control. So you can't just say, well, the east half of the city gets cached, the west half doesn't. That's not going to work. So you have to have an experimentation platform that intelligently randomizes things, or at least non-intelligently randomizes. The main point, it's got to randomize. It's got to do one thing, it's got to randomize. So keeping control group also allows us to see if what we ship is causing a regression in metrics, aka breaking the app. So what we do is something called a staged rollout, and here's where Scala comes in. Instead of just shipping the feature, we basically will ship it to a little bit of users, gather data, and then once we are reasonably sure that we are not causing regressions, we will give it to a little more in stages. This is how we don't have outages, instead of just, okay, 50-50, let's see what happens. And the cool part is, ideally, engineers do unit tests and things are fine, but when you ship things into different markets, some things happen. And so this stage rollout allows you to safely roll out features and not just see if features are giving you a business impact benefit. And so how this actually works is start, collect data, then you see, is it working? Okay, if I know early on, no, causing crash, okay, stop, roll back the experiment. Okay, yes, move to the next stage. Do I have enough to safely say, no, okay, keep collecting samples? And so we have to have so we're performing statistical tests the whole way through this. And so the architecture, before I go into a little bit more, is you have your experiment logs, which is who's treatment, who's control, or who's treatment 1, treatment 2, treatment 3 control, if you have multiple variants. And then your mobile events, which is basically, were people able to go through the flow? Download the app if they're new users, request a ride, get a dispatch, get a ride, get into the car, get dropped off, rate their driver rates them. So we look at these and let's see the percentage of sessions with the trip. And then we have some sort of algorithm, or it's just statistical tests, and we see if this is safe or not to roll out. So how do we test? Here's maybe data scientist's favorite XKCD with the jelly beans. If you haven't seen it, it's a good one. You probably can't read it, but basically they're like, hey, keep testing the different colors. And if you have a 5% confidence, if your p-value is 0.05 and you do 20 tests, one of them will probably have a false positive. So it turns out, yay, green jelly beans, acne, scientists. So initially we use these kind of regular t-tests. They're not designed to be done okay, peak, 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 peak. Yeah, at some point you're going to get a false positive. So we tried what's called a sequential likelihood ratio test, but we realized, we're assuming that all of my trips are independent, when clearly that is not the case. I go to the same places, I have the same phone, I'm in treatment or control. Hopefully that doesn't change. If we do, we have problems. So now we have this sequential likelihood ratio test, but instead we use something called a delete a group jackknife variance estimation, which is a very fancy and warlike way of saying you do a simulation, and through that simulation and clustering users into different blocks, you are correcting for the fact that all of my trips are not independent. But now we have to do a simulation for every experiment for all of Uber every time we want to peak. So this is quickly becoming a large burden, and Scala handles this very well. So this is how we are able to ship features to meet business needs without compromising our reliability. But it also allows us to move quite fast without breaking things. So then my computer goes, good. Clearly my computer wants my presentation to be over. All right, so as an example, in the top one, things are fine. We don't have a lot of data. Our confidence intervals shrink as we get more data, and it looks like, let's say 0, the percent difference from treatment and control. Let's just say like how many writers successfully take a trip in a given session. And then in the bottom, we see, look at 0, the 0 line. It is within the confidence bound, and then it becomes apparent as we get more and more data and those error bars shrink. Yeah, we have a problem. We need to roll this back and see what's going on. And let's look into the code some more. So that is how we do experimentation without having things break. But ideally, we want our features to do more than not cause Uber to crash. Presumably, we built them for a reason, and we want to know if that reason is good enough to keep them. In the case of cache, because there were serious costs, right? So we pick a metric. When I do this, I usually start by saying, okay, if I had a video camera in every trip and I had all information, what would I want to know? Okay, what is the next best thing? What can I actually track? And let's put in some instrumentation if we aren't logging those things. In this case for cache, the story that I put to you was we want to allow people who could not otherwise take Uber to take Uber. So presumably, if I give the treatment group access to cache, I would hope that more people in that would successfully take a first trip, like in the example that I put. So let's say my metric is maybe how many new riders I get, or the proportion of downloads to new riders, or signups to new riders, something like that. I'd also have various other metrics I would test, but that's going to be my main decision metric. Now, I used to do this by hand before our implementation of this Scala statistics engine, which I like, which basically means I run Hive or Spark, I get the data, see who's treatment control, look at my metrics, write a Python or an R script, do statistical tests, check a bunch of things, make some charts, do a write-up, paste that into Google Doc, or generate an HTML output through R Markdown, host that, and then send it to people. And that's just for my team in which I'm embedded. What if you're a team without a data scientist? I mean, most things are straightforward, but it quickly, as long as things work great the first time, it's OK. You can just paste code from Stack Overflow. But if you don't know what you're doing, then you can quickly have experiments that you think were successful or not successful and make very costly business decisions. So basically, the turnaround time was a lot of time, particularly for teams outside of San Francisco who didn't have a lot of data science resources. So with our statistics engine now, we have our experimentation logs and our metrics, like our cache new users in Hadoop. We bring a subset of those into Vertica, which is very quickly queryable. Then we have our Scala-based statistics engine. And by based, I mean written in Scala. I'm not sure why I said Scala-based, which is going to do a lot of this stuff. And then we have a web UI, very friendly for non-technical people to just say, I'd like to run this experiment with this metric for these users, go. And they can immediately know, say they just want to send emails, they want to test a copy. Does this make people download Uber or not in Chicago only? I don't need to have a whole data science team to know this. I just need to do one t-test, but I don't want to set up the whole infrastructure to do this. This allows that to happen, and Scala is what allows this to happen on demand. Because if you think about it, here's what they get. It's testing for a bunch of things I'll talk about. You can see at the top these 3 check marks. We're testing for flicker, which is hopefully if someone's in treatment, they should stay in treatment and not go to control. That would be bad. That would bias our experiment, and they would not be happy if they were planning on using cache and then couldn't. That would not be great. Do you have pre-existing bias? And are my sample sizes balanced overall? Then you can see here we have our control and our test. What was the actual metric blurred out for your convenience? I apologize. What was the percent change? What was my sample? What's a sample I needed to have an appropriate level of statistical power, which is basically how confident I am that I have actually detected a true effect if there is one. And all of this is just created on demand for them. No more scripts, charts, pastes, hosts, exports, although I enjoyed doing those things, but it took up a lot of my time. So what this Scala statistics engine is actually doing is actually quite a lot, and it's doing it very quickly, and it's doing it on demand. So let's walk through our example of cache. We validate the data, make sure that I don't have users changing groups based on my logs. Then, depending on whether my metric is continuous, like a continuous variable, like how many trips did someone take, a ratio, like what was the percent of trips which had a tick, where someone filed a ticket, where there was a defect, what's the defect rate? Or a proportional, which is, you might just call it categorical, like did you take a trip or not, or did you take Uber Pool or not, or did you tap on this thing or not? Depending on the metric type, we have outlier detection, and then we have something called the Cupid method, which was sort of made popular by Microsoft, and the name is fine. It stands for the, I think it is controlled experiments using pre-experiment data. So they sort of picked and chose their letters there. But it's really good for, if there is pre-existing bias, it is essential. And then if you want to reduce your variance so you don't have to have as many samples, which by the way, for Uber, unlike a lot of tech companies, we exist in the real world. If you're doing experiments on Facebook or Google, I've talked to data scientists there, and they're like, yeah, I have as much sample as I want, all day. I only have so many drivers in Cairo, Egypt, that I can use for my experiment. And so the gains from this are they're non-negligible that I get from this variance reduction. So then, I won't go into all this math here, but basically, it's a lot of checks. It makes the experiment results more robust, and it is done correctly, on demand, every time, no matter who uses the UI. And even among data scientists, because what do you mean by t-test? What do you mean by statistical significance? We're using different packages, which might have different assumptions about the distribution of the data. So this is great. Then we calculate the power, the lift, and we output the result. It's right there on the web. It's shareable. It's fantastic. So Scala is allowing us to, first of all, roll out features that we need, that this guy in Mexico needed, without breaking the app and compromising our reliability, and also quickly testing if this is actually working, and so we can roll this out to more people on demand, which is very nice. So, was cache successful? Did it work? Well, I'm on the cache team, so spoiler alert, yes. Yeah, it actually worked great. In fact, it was so successful that in some markets, we just defaulted everyone to cache. We didn't even ask for your credit card. Initially, it was enter a payment profile, and you could say enter your credit card or cache. But as anyone who's done sort of user acquisition knows, the more friction it is, I mean, you think it's just one more screen. If people really want to ride, they'll get one. But people drop off. If they've never taken Uber, they're like, this is too much. I don't want to enter my credit card. I don't want to open my wallet. Come on, I'll just take the bus. That happens, It is no joke. And so this worked great. It allowed people who didn't have access to Uber to have access to Uber. It expanded Uber's geographical reach, because where do you think credit card trips are? They're not just sprinkled throughout the city. They're in the city center, where the financial district is, where business travelers are. So people that live on the outskirts, they don't have a credit card. And you think drivers are going to go there knowing that no one with a credit card is there? No way. So it sort of opened up a lot more of the city, and it allowed Uber to launch in other smaller cities where there weren't enough business travelers or credit card holders to justify demand. So this was a big deal for markets like Latin America, India, Middle East. And then, yeah, we have the frictionless thing. So it was great. The thing is, if a rider does have a credit card or debit card that we take, we still want them to use it. Why would we want that? Well, there's a few reasons, so they can have the magic of Uber. I mean, I say that somewhat facetiously, but it is a real thing. When you're thinking about taking a taxi versus taking an Uber, it's kind of a different animal. So we want them to have that if they have a credit card. And also, coming back to that problem of that whole, we're a business and we need to collect our service fee, normally what you do is, in a credit card trip, a little bit of that money is routed to Uber. Most stays with the driver. On a cash trip, the driver just keeps all of it. And then on the next credit card trip, Uber takes a little bit more, and then they're square, and it balances out. But if all of the driver's trips are cash, then the driver actually starts to owe Uber money, which is kind of a weird situation, but can happen because then you're in a situation where the driver actually needs to go to a convenience store and like wire Uber money, which we don't want them to do that. They definitely don't want to do that. And that's less time they can be making money in the first place, right? So actually, a little bit of credit card trips goes a long way. If they can instead just have a rider with a credit card go to another area where other riders are, that's way better than them having to wire Uber money. Because Uber is not just trying to like squeeze drivers. If Uber doesn't make any money in this small city, they cannot be there. And that means what's really non-magical is no transport at all. So this is why we're saying if we want people to have credit card trips, if they have a credit card, we want them to use it. So it would be cool if we could intelligently decide who should just get cash so they can sign up quickly, and who maybe has a credit card and we should present that to them. And how would we intelligently decide this? Machine learning. And Uber's machine learning program, appropriate for Florence, is called Michelangelo. And so now, in our agenda, we will go to how we use Scala in machine learning. And this part's pretty cool. But before we talk about what we do now, we want to talk a little bit about the architecture of our machine learning platform and how this helps our user and how this helps Uber to deliver the product to the people that use it. So let's rewind to a few years ago. Now, here's the sort of traditional machine learning lifecycle. You have to get the data, you have to train a model, you have to pick which model, because you're doing different iterations, evaluate it. You have to manage the models. In my last job, the way we managed models was spreadsheets. There was no version control. It was just spreadsheets, because the expert witness, the real expert witness, would be like the chair of the Stanford econ department, but they don't have time to actually write an expert report because they have to teach and do the research. So they would come to my company and say, hey, get this data, try this model, and see what happens. So then my boss would say, hey, Nick, get this data, try this model, try it all these different iterative ways. Here's your spreadsheet. So managing these models is no joke. Then you have to deploy, actually to predict, and then monitor to make sure things haven't changed and the stuff that you trained on is still representative of what's actually going on. So the problems that we saw back in the day, 3 years ago in Uber is a long time, so it was back in the day. Basically, it was super fragmented. Each team was building their own solutions, which was leading to a lot of cognitive burden, hard to maintain systems, they were unreliable, and basically a lot of people were doing the same stuff, just different enough that no plugs could connect to each other. So it was also, we would train our models in Python or R, and it was good to prototype. We'd say, hey, this is going to be great, we should invest in this, but it didn't really, you can't just shove 1 million trips a week into your R library. It won't fit in memory, it just doesn't work. So it's also not reproducible. You would train the model, this is great, and then you're like, who trained this? Look at this coefficient. No, and then things have changed, and it's just, that data wasn't stored. It was just some CSV somewhere. So it was tough. So here is what was built, which is Michelangelo. Michelangelo. You're here. Good? Yes? Okay. Mic's on, apparently. So it's self-service. It allows you to do all these things. It's based on Spark and MLlib or MLlib, and some other open source tools and some other proprietary stuff, which are really just forks of other open source tools. So large data sets, centralized feature store, which is awesome, which I'm going to talk about, is where Scala really comes in. And then model analysis, and then real-time predictions, which, as we talked about, offline batch, that was bad this morning. I just kind of my whole talk's about batch and online, so. We still have batch. We still have offline. It's okay. Let's talk about offline batch first. So we have our data lake. Then we have a Spark or SQL job to prep. Remember, we have our get data, train the model, evaluate, and then deploy. Or in your case, this way. And so that's going into Hive, our feature store, and then keep our outcomes for the training set, our labels, right? And if it's online, we have Kafka going to our stream engine, and then that's going to Cassandra, so that because you can't really query Hive in real time. So we put those things in Cassandra. And then for training, we currently only have offline training. you'll train your model, get your coefficients, and then you'll put that online to be able to call. We are developing online training, and you might think, well, why do you need online training? Well, if your model is causing things to happen in the ecosystem, and that is changing things, then your model is now endogenous to the ecosystem. And so you now need to have a different mathematical approximation of the way the world works. So that is coming. All sort of this model object is put in Cassandra, and then you have either batch predict for offline Spark, and then you have real-time predict service where you have your trained model, and then that is called by a service. The service says, hey, this model, this user, here's your features, give me back a result, I'm going to do something with it. Or those features are just sort of those predictions are put into Hive and Kafka, and they can then be ingested by their services, or maybe not services, maybe just analysis, kind of done on a flat file. Then you also have this monitoring part where we sample some predictions, and then we check to make sure things are going well, and this is kind of baked in to monitor. And then, as you step even back, I know, right? We have an API, so you can run this. We have a web UI, which is actually quite nice. API doesn't really give you these charts, but you can use Python or Java to talk to the API, to keep track of your models, to choose your models, and then you kind of have this whole monitoring situation going on. So, coming back to Scala, we have this feature store, which I love so much as an actual practitioner. And the reason I love it is you work on cache, and I'm trying to think, OK, I have features for my model. What would be a signal to me better than random that someone might have a credit card? Well, maybe where they signed up. Are they in the city center? Are they in the outskirts? Right? What city did they sign up in? What country did they sign up in? If they're in the US, rather than average chance. If they're in Germany, maybe below than average chance, right? Cache is a thing in Germany, very much so. So, but other teams know. First of all, they've already done this stuff, which means I don't have to do it, and I also don't have to do it wrong, because there's a lot of domain knowledge that goes into these metrics, and if I'm trying to, finesse my model, and I'm actually using a feature that is incorrectly engineered because, I've never worked on that thing, and someone else has, why don't I just use theirs? And this is what is awesome about this. So we have this centralized feature store, and the features are selected by a join key, because we have different entities at Uber. You have riders, you have drivers, you have restaurants, you have eaters, you have cities, you have freight, routes for Uber Freight, which is like trucking. And so we have a Scala DSL to do this, a domain-specific language, to do this feature engineering and selection. And this is awesome. So I want to write a model, and I say, OK, I want to use this algorithm, and I would say, I will bring these features to the table that I know about, because I work on them. Also, I would love to just have my shopping basket and say, I will take how many trips they've ever had, what city they're in, how they signed up, were they a referral, were they actually a driver taking a ride, did they have a promo, were they organic, did they click on paid marketing? Those are all things that could influence this, right? OK, I'll take this in my shopping basket, and I just put it in. Also, it allows me to transform my features right there, say, I'd like the max of this, or I'd like the average of this over time. I'd actually like both how many trips they have overall time, in the last week, in the last 2 weeks, in the last 4 weeks. And I can just easily do basic arithmetic on that in this DSL. And so you can call them both from palette. It's the feature store is called palette, because I'm like an artist, just making my models, a code artist, you might say. And so I'm saying I want palette. It's a rider. It's not a driver or a city or an eater. And then it's in this sign up info. It's called just a feature group, and I want this one, and I'm going to join it on the UUID. Also, I'm probably going to have a lot of missing values for some of these because they don't apply to all riders, like for new riders. If you're brand new riders, how many trips have you ever had? Well, none, right? That field is null. So I can take the mean. I can do lots of stuff with this language. And can be for both training and also prediction. So if I'm using this feature store, the pipeline for offline training, and by offline training I mean the only training that we currently have, but I still think it's cool. You have your Hive data lake. You go into Spark or SQL of some kind. I have my basis features, which are the things that I bring to the table, which I have calculated through using Spark jobs. Remember, just keep our example in mind, okay? I know this is kind of abstract, but this is all just so that we can do stuff for users and make the experience better. So my basis features, I put those in the feature domain-specific language, which, let's say, my things I calculate are like, the cool part about this, too, is I can use any other model outputs as an input to this. So I'd say I have another model deployed for whether I personally think they have a credit card, and I'm going to ensemble these guys together. There we go. So I have that. Then I have my feature store in Hive, which is everything every other data scientist at Uber has ever done and put in there. And I can just go shopping there or go painting there, because it's a palette. Again, appropriate for Florence. I put those in my feature DSL. And then I transform those, put them in my training algorithm, and then I have my model output. So this is for offline training. Now, if I have online serving, which is what I'm actually doing, because remember, coming back to our example, what I'm trying to do here is I'm trying to predict whether I think a writer might have a credit card and whether I should even show them the screen, hey, enter your credit card or choose cash, or just let them keep going and get on their way. Because when you download Uber, it's almost always because you want to go somewhere right now. You're not just like, oh yeah, I guess I could take a trip here. Like, you may already be late because your bus already broke down. So you don't want to dig in your pocket and enter a credit card, especially if you don't have one, right? But I want those credit card trips if I can get them, because they allow me to continue to operate in this region without having to have drivers stop, go to 7-Eleven in the US, other convenience stores in other countries, and just wire us money. So I'm doing this online because they download the app. They are, this is like the fourth click they have ever done. So I don't have time to I have nothing to pre-calculate. This has to be online, right? This has to be right then. So what I have is I have my basis features and my Cassandra features, which I have calculated already. I'm computing these every day in Spark, and then I'm pushing them to Cassandra so that our team service can just call Cassandra right there. And through the feature DSL, transform them, and then I serve this model up. And here is what is so cool about this. Now, as a data scientist at Uber, we really want to have machine learning models in production. That's the dream. We want to think, okay, I can, fresh off my Kaggle competition, I can just use my modeling and benefit mankind and Uber, and the app is going to make decisions based off my model. The thing is, if you want the Uber app to do something based on your model, it takes a fair amount of engineering resources, right? You have to have at least one backend engineer to be able to interact with your model and do something about that. And then you have to have probably an iOS and an Android engineer to actually do something in the app based on that, unless everything is just straight from the backend, which is unlikely if you want to have anything custom. So you already have to have a fair amount of engineering for something that, and I have to say, no, I promise, this is more important than whatever you're doing. I'm sure you don't have anything to do right now. So the reason this feature store and Scala DSL matters is because now I can say, look, here's a model object. In the backend, just call this. And I can now, because Michelangelo has all of my features in Cassandra, all of my model parameters in Cassandra, I can now just go nuts. I can change the algorithms. I can go from like a XGBoost to deep learning or logistic regression or whatever I want, change the features, change everything, and I just say, oh yeah, could you update that model ID, which is already configurable just right then. You don't even have to land any code. And then that takes zero overhead. So I've got this already deployed, and as a data scientist, I can just continue to iterate without slowing the team down or having them to have to do a bunch of merges every time I want to test out a new feature. So this is super powerful, and it allows us to use machine learning in a lot of things that we couldn't before just because it was such an onerous process. So yeah, this is why it's helpful. Now, think about this. Partition models, OK? Let's say that I suspect, remember, my motivating example is I like cash, I want people to use cash, but I want the credit card trips that I can have so that drivers don't have to wire us money, right? But let's say that I suspect that some of my features are different they vary by country, like the relationship between this particular feature and whether the rider might have a credit card. They vary by country, or maybe even by city, right? So I could include an indicator variable in my model for country and city, and I have to interact that with everything. That would get hard, especially if I don't have a lot of data, enough data to really sort of detect the parameter for each of those cities. So what I really would want to do is I'd want to actually have a separate model for each city, or let's say a separate model for like each Uber X, Uber Black, Uber XL, things like that. But it's hard to do that, and it's also hard to bootstrap models if I have very little data. And unfortunately, the places in which I have little data are the places that I suspect actually might differ from the norm, often. So instead, we have this hierarchical partitioning, which is handled elegantly by Michelangelo using Spark. And we are automatically going to train one model per partition. And then we can deploy it as a single unit, as a single model. And here's what that looks like, OK? So we have our partition scheme. We have global, country, and then city. Let's just say this is our example. So then we make a train test split on global. When you're doing machine learning, you normally keep most of your data for training. And you say, OK, optimize this given this objective function and come up with some sort of parameters, test hyperparameter search, and then look at your test data and see if you were right. And never, ever mix your test data with your training data. So this is what you do. So we have that train test split globally. Then we're going to go ahead and keep that for all the partition levels, right? So that's this little line here. Then we'll train a model for every node. So I have my global model. In addition to that, I have my country model. In addition to that, I have my city models. Then I prune the bad model. So let's say, oh, in this city, in Aguascalientes, Mexico, I just didn't have enough. My maximum likelihood estimator didn't converge, or I just don't really believe it, or whatever heuristics I have to say, I just need to scrap this one. Then I am choosing the best model for each node, right? So I can do in this city, in Jalisco, I can do this, but it turns out for like Costa Rica, I just have to do all of Costa Rica. In any given city, I didn't have enough. So I'll just do all of Costa Rica, okay? But I can do for this city, or say like, I can do Jalisco, I can do Mexico City, but I can't do Aguascalientes. I just have to do all of Mexico for Aguascalientes. So I fall back. But it doesn't force me to do all cities just as one big aggregate blob. I can still use the more specific recommendations of that city when I can, but I don't lose Aguascalientes. I'm not just like, sorry, I have no prediction for you. So this is how it works. And then that is Michelangelo. So last part about Spark magic, which is sort of unrelated to a motivating example, although you can think about it this way. Say we like cash, it's getting new riders. Okay, lots of people are using Uber that didn't use Uber before. But there's a cost to this, right? Like we talked about, There's a cost to them because it's not magical. It's really not magical? Not having a ride at all. So clearly they're willing to, deal with having to pay, with the paper money, which is the only way that they pay. So I don't really care about that. But, drivers have to wire us money sometimes. It's sometimes riders run. What if you're like, oh, sorry, I thought it was 10. Sorry, I don't have 20. What do you do? So there's a cost to this, right? So let's say I'm getting all these riders, but how performant are the riders? And by performant, I don't mean fast. I mean, Like essentially, are they going to take a lot of trips or not? It could be that cash writers, they'll take a promo trip. A lot of times you get, your first ride's like $10 off or 10 euros off, but then they'll never take a trip again. Okay, so let's say I wanted to calculate for each user, individual user, what their lifetime value is for Uber over the next 2 years, or just say indefinitely. That's a lot of riders, okay? And say I have this kind of hierarchical model I'm going through, but I have to do tons of data prep before that. An enormous amount of sort of feature engineering data preparation on all of Uber's riders, okay, to see if cash riders are categorically different than credit card riders. Because my guess is the business travelers who are going to and from the airport and they're not even footing the bill, they're probably not paying cash, right? So I want to pick this up because I have to make a business decision about should I spend money to do marketing and roll out cash to this new city, or should I spend it on something else, on like self-driving cars, let's say. So to do this modeling, and specifically the engineering before I can feed the data into this model, I'm going to use something that is called Spark Magic. Spark Magic, it allows you to, from a Jupyter notebook, which used to be called an IPython notebook, it's a very common sort of IDE for data scientists. It allows us to execute code in a lot of different languages, do charts, do models, ship stuff off. It's pretty common. So from Jupyter Notebook, I can write code and SQL queries, and using Livy, which is this API between the Spark cluster and the Jupyter Notebook, I can sort of manage my Spark jobs, and also I can write. So normally, if we want to do something like this as a data scientist, we'll probably use PySpark or Spark R, because we generally work in Python or R. I mean, we don't really do a ton of just straight analysis in Scala, although we do have Spire, but it's just R is made for math. Like that is its purpose. So it has a lot of tools that Scala just doesn't. But if I have to manipulate this immense amount of data, and I am using PySpark, like I'm using a Python or an R interface to Spark, I still am constrained by the imperative nature of those languages, right? So I can't use the full parallelization of Spark to do this preparation. But if I can just do straight Scala, then I can. And even better, if I can do straight Scala from my normal environment, and then I can ship that up to do some analysis right after, because you can do Python, pandas, charts on top of this. That's quite a win for a data scientist. And so this is another pretty cool thing that we have that allows us, so if we wanted to calculate this LTV, let's say, for user, to see should we keep this cache thing going, we could use Spark Magic to do all of our data prep and modeling for this to see if these users are in fact helping the business so that we should keep going with this, or should we just take that money and put in self-driving cars because we know where that's going. So this is what we have. Like I said, not constrained by imperative language. I just got a little excited. And that's it. So questions, and then Uber. Thank you.
Hi, I have a question not about Scala, but about the app development. So when you want to kill a feature or introduce a new feature, how do you do it in practice? Do you need to update the application? You maybe mentioned something about the configuration. Is it just, can you do it like without touching the iOS or Android app easily? Or do you have to wait for an approval in the App Store or something like that? It sounds like you want to iterate quite quickly here, so that could be problematic.
Yes, exactly. So your question is, if I want to iterate, meaning either add a new feature or deprecate a feature, do I have to wait for a build cut, basically, right? Yes and no. And it really depends. If it is entirely powered by the backend, then no, I can just do it right now. If it is in the client code, then yes, I have to wait for the build cut. And that's why when we're doing experiments, shipping things, like, okay, make sure to get this I just had something that was, the translation was off in Saudi Arabia. It wasn't working, so we had to get that localization in so that it could make the Android cut on Monday. But if that was just totally driven by the back end, yeah, then I can just change that code right there. But so yes and no. A lot of experiments are rolled out through the back end, and the client is just sort of receives what the back end says. But there's some stuff that is just in the client code. And so yeah, that's definitely a pain point sometimes, but yeah, it's part of development. Good question.
You talked about A/B testing, and since your app is very ubiquitous, very present, do you have any data where nearby users got one in the A group, one in the B group, and they figured out?
Yes. Yes. There are often WhatsApp groups of drivers. It's more common with drivers than riders, because you ride Uber, you don't know each other, you're not like, hey, it looks like you have something different. But yeah, drivers might say, are you guys seeing this? Right? And so yeah, that can lead to, I mean, it won't necessarily bias your experiment, because the users are, they're still randomly distributed. And so it's not necessarily the case that a disproportionate amount of treatment or control users would be a member of those groups or be alerted to that. But it would be not great for the user experience if the driver says, well, why didn't I get this? Or if it's a feature they didn't like, saying, how do I do this? This also happened when we rolled out the new driver app. And some drivers didn't like it or did like it, and they would sort of uninstall, reinstall to try to get in a different treatment group. So we had to correct for that. But yeah, that you do have that sometimes, but that is just part of having a digital company and a real physical company with real people that move real things. Just we're in the real world, people talk to each other in the real world. It doesn't really bias our experiments, that's just part of it. But that's another reason why, if that does happen and we say, this sort of half and half setup is really not ideal. We want everyone to have this. That's why things like the variance reduction from the QPED method, or being able to iterate quickly using the Scala statistics engine, allow us to move a lot faster, so we can say, okay, do I have enough data, do I have enough data? Yes, okay, go, ship it to everyone. Through the staged rollout, mind you, so we don't cause crashes. So Scala is really helping all this move forward for exactly that point. Yeah.
Hi, thank you for presentation. I have a question about your architecture. Is the reason why you choose Livy and Jupyter instead of Spark Job Server and Apache Zeppelin?
So you're talking just about the last part? The question is, why do we use Livy for Spark Magic instead of something else?
Spark Job Server, and why you choose Jupyter instead of Zeppelin? Did you try Spark Job Server or Zeppelin?
I don't know that much about that decision. I do know that Jupyter notebooks are, so as data scientists, it's pretty divided between, most people like both R and Python and just kind of use whatever. The Python users prefer Jupyter notebooks. That's just kind of what they know. And so we have a service called Data Science Workbench, which allows you to quickly spin up a remote, either RStudio or Python Jupyter notebook session, or Spark, or whatever language you want in Jupyter, just in a Docker container with all your environment, so it's there and ready to go, and you don't have to do anything locally. And it's continually updated, so you don't have to deal with libraries or dependencies. And I think because they already had that going for Jupyter, they just said, hey, let's just do this for Spark Magic as well. We can use Livy. I think it would have been perhaps more difficult architecturally to implement those other solutions, since we already had this going for Jupyter. But I started guessing about 20% into that answer, so I can't really say anymore.
Okay, thank you.
Yeah.
Any more questions? Okay, thank you so much, Nick.
All right.